Thanks everyone for showing up for our Friday seminar series. And thanks Dr. Munawar for uh, being on our Friday seminar. So just for you to give an introduction about Dr. Asim Munawar, Dr. Asim Munawar is a project lead at IBM Watson Research Center in New York, where he is at the forefront of advancing IBM's in-house LLMs for enhancing reasoning and planning capabilities. With a distinguished 12-year tenure at IBM Research, Dr. Munawar has held pivotal roles, including manager and program director for neurosymbolic AI. He earned his PhD from Hokkaido University and has since led multiple groundbreaking research initiatives in deep learning. His primary research focus is on pioneering next generation AI by integrating symbolic reasoning with machine learning techniques. Dr. Munawar has authored over more than 60 publications in leading journals and peer-reviewed conferences. He also served as a board member for PACT Publishing India and the National Center for Artificial Intelligence, NCAI, in Pakistan. So thank you, Dr. Munawar. Over to you.
Thank you. Thank you everyone for joining, and special thank you Shaswata for inviting me to the seminar. It's a pleasure. I know it's always good to be there in person, but it was difficult for me. So anyway, I'm still very happy that I'm able to give this talk virtually. So I'll be talking about reasoning with large language models. This is a topic that is in the main media also. There is a lot of debate going on whether LLMs can do reasoning, they cannot do reasoning, what reasoning is actually. So I'll be talking about that. Before I start with my presentation, I just want to clarify a little bit of terminology. Foundation model versus large language model, they both have slightly different meanings, but they are very frequently used interchangeably. Um, so the idea here is that from a lot of data, internet scale data, we train a base model that we call foundation model, and then we can repurpose that model into many different large language models for various tasks. Okay, but as I said, these terms are now used interchangeably, and allow me to do that also throughout this talk. Okay. I'll start with a brief self-introduction. Shaswata did a very good job already, so I don't need to spend time on that. My motivation, what inspires me to keep working in this area. I'll explain what LLMs is. I know, like, I believe many of the audience already know what LLMs are, but just a very brief introduction to that. Reasoning, what does reasoning means, what does reasoning with LLM means, what are the new trends that are upcoming. Okay, so then I'll briefly talk about agents going towards neurosymbolic approaches, and then I'll discuss IBM's take on LLMs at the end. So, so the left hand side was already covered by Shaswata very well. So my research interest basically lies on the right hand side, neurosymbolic AI in the age of LLMs. Um, so neurosymbolic AI is where we try to combine systems that are symbolic and systems that are neural, data driven versus symbolic systems. Okay, so stochastic versus symbolic. Humans do it seamlessly, and we hope that AI systems will be able to do that. There is always a trend where one of the system, either symbolic or neural, takes most of the resources, most of the attention, but we always tend to keep coming back to these neurosymbolic methods. So that's my main focus. And right now I'm working in improving large language models on reasoning tasks, and my interest goes beyond just language model in other applications also, other applications of AI. So what keeps me motivated is basically the idea that we'll have such robots working around our house helping us, And this is not something that I thought of right now. I know everyone wants these. Um, when I was a kid, like around 6 years old, my father told me that we will have this kind of robots within 10 years in our home. And I remember whenever I used to make my bed or do like clean up my room, I always used to think that it's just for 10 years. Like after 10 years, I'll not have to do this anymore. I'll just get one of these robots and my life will be very happy. So, uh, 30 years into the future, and this is what we have. Okay. So, you see, there is a big difference between what was promised to us and what we have right now. Um, and this is the difference that keeps me motivated to work in this AI area, robotics area, natural language, vision. And whenever a new technology comes in, I always, in my mind, think how close the left hand side future is now. Okay. And LLM was a big jump in that direction. LLMs are not the whole solution, but they are definitely a big part of the puzzle. Okay, with that, let me briefly explain what LLMs are and at the same time what they are not. So, there can be some wrong expectations we have from LLMs, um, that should be clarified also. It all started with this paper. It's called transformer architecture. Most of the models are based on this architecture, although recently we have started to see some new architectures also. This is attention is all you need versus some other things that we used to have before. Now we don't have. um, so to understand attention, attention is just to let the model see the whole input and let it take the part of the input that it wants to focus on while it is generating some output token or focusing on some output token. So, in the examples that I have on the upper left side, the animal didn't cross the road because it was too tired. In this case, the it refers to the animal. In the next sentence, the animal didn't cross the road because it was too tired. So, it when it's looking at it, it will focus more on the street, not the animal. Okay. So this is what the attention allowed the models to do. And similarly with images, when it's generating a particular word for caption, it focuses on that particular part of the image. Okay. So this is what the attention allowed the models to do. And later we found that we can stack them and we can make them like multi-layer and even apply them to natural language at a scale that we never imagined was possible before. Okay. So on the right hand side, like this is how we use large language models. We give a sequence of input words or tokens, let's say words. Okay. And the words get encoded, and then we have a decoder part where we expect the decoder to spit out the next word. So when we ask what is the capital of Japan, we expect most of the LLMs who have learned this during training would say Tokyo as the next word or token. Okay. So there are like LLMs with more fancier architectures, encoder only, decoder only, and some combination of these. But this is what they are doing. They are predicting the next word or next token. That's it. That's all LLMs are doing. They just understand what should come next. And this the main component. Of course there are other components like positional encoding. There are multi-head attention, but the main component is self-attention component, where what we are doing is we are training the model in a way that it can understand what QKV is: query, key, and value. Okay. uh, Query, you can think of it as a question. A key, you can think of it as a field name or a column name, and value is the value that needs to be retrieved. So in this example, if I ask what is the full name, it needs to extract the key name, and it needs to extract the value from that, um, which is my name in this case. How they magically become q, k, v? Because we train it like that. We train these matrices wq, wk, wv, um, to become like key, q, um, query, key, and value. Okay. As I said, this is a very simplified view. We stack those on top of each other. We use positional encoding. We use multi-head attention. So a lot more is going on. There is an embedding layer, which needs to be trained sometime. So a lot more is going there. But basically, this is what the models are doing. They're just predicting the next token. So let's look at reasoning with large language model. On the right hand side, I just gave an example I ran few days ago. I just checked whether the area of South Africa is larger or smaller than Pakistan, and it gave me the reasoning which is contradicting the table that it generated the next. Okay, so it says Pakistan is larger, but when it spit out the number says the other story. Okay, so there are issues with reasoning with LLMs, but anyways, I'll try to explain what they can do right now. So before we talk about reasoning, we need to define what is reasoning. Okay. So reasoning in this context is simply a process of thinking in a systematic manner. Okay. Any kind of explanation we can give for our answer, um, especially step-by-step explanation, not a huge single sentence explanation, is considered to be a reasoning. So there are two types of reasoning: formal reasoning, which is very mathematical, very symbolic, and natural language reasoning. Okay, so before LLM, mostly when we talked about reasoning, we were talking about formal reasoning. Recently, the reasoning word is used more for natural language reasoning or informal reasoning. Informal reasoning is like human like understanding, human like reasoning. It can be subjective. Two people can give different reasons for the same thing. Okay, that is what LLMs also do. But as long as it all makes sense and we get our final answer which is correct, we should be happy with it. Okay, so that's what's going on. And so we'll focus mainly on natural language reasoning. We will not touch formal reasoning. There are papers that clearly say that LLMs cannot do formal reasoning, at least any complex formal reasoning. Okay. um, Early on in this LLM journey, we had a paper where it showed that reasoning is what we call emergent property of LLM. So emergent property is a property that does not appear in smaller models, but it start appearing after a certain threshold suddenly. And these plots, if you see, you don't need to understand the plots, you just see there is a sudden change at some point in time. um, and the size of the model alone is not responsible. There are other things like training data quality, number of training flops, size of model parameters, of course. But now it is debatable whether reasoning is an emergent property or it exists even in smaller models with lower quality data. But anyways, just to put it there, it can be considered as an emergent property of LLM. As I said, so what reasoning is doing here is it's giving an explanation of the outcome. It's giving an explanation of the decision that is made by the LLM. Okay. Um, and we like that explainability. Humans don't like when someone just gives us the final answer. We want the whole story. So for looking at the deep neural network or LLM, there are two ways to explain that. One is global explainability, where we kind of explain overall what the model is trying to do. um, if you have seen before on the left hand side, these filters used to be very common. What a convolutional network have learned, um, like how it is looking at the images. There are edge detectors, and then there are second layer, and what third layer is doing. So this is global explainability. And local explainability is where it is trying to explain a single data point, single decision that it's taken. So the reasoning, in context of reasoning, we are always talking about local explainability. We are not saying that this reasoning will explain overall structure of the model by any means. Okay. So just that instance, just that output, it will be, it will try to explain. Okay. Yet another concept that I believe we need to understand before moving forward is thinking fast and slow. Okay. Um, so there is this book which I highly recommend you to read by Daniel Kahneman. It's called Thinking Fast and Slow, and there is a concept of system one and system two. This is how we perceive the world. System one is basically intuitive. It's 95% of the tasks that we do unconsciously. We see something, we immediately understand it's a white circle, it's a washing machine, it's a car, it's a person. We don't put we don't put intentional explicit effort into that, right? So that's kind of our autopilot mode. Most of the time we are doing system one task, but system 2 are definitely, like, they're 5% of the tasks that we do, but they're extremely important for our intelligence. Okay. So here we have to take it slow, we have to gather information, we have to think step by step. For example, oh, okay. For example, if I ask someone to plan a vacation, that is not a system one task. Nothing comes to your mind immediately. You have to ask many questions, you have to think a lot, you have to understand how many people are going, what are the preferences, what is the budget, um, and so on so forth, when are the vacations. Okay. So on so forth. Okay. The advantage will be that any system 2 decision can be explained. Once you will reach some decision, if I ask you how you reach that conclusion, you will be able to explain. System 1 decision come to mind immediately, but you cannot explain them. um, you just recognize them, right? So they, in real life, both of these go hand in hand with each other. We cannot differentiate them. We, most of the time, we don't understand that they're working together so seamlessly in our mind. For example, in this picture on the right hand side, which car should go first? You need to first use system 1 to perceive the environment. Is there a road traffic sign here? What are the agents involved here? And then with system 2, you need to understand where you are, what rules to follow, and so on so forth. And then you can make a decision which car should go first. um, with that, let me go into the reasoning with large language models. And chain of thought reasoning is the most common method. um, and I believe it's the most basic method also. Everything builds on top of this kind of step by step reasoning. Okay. So chain of thought reasoning is, um, basically, instead of asking the model directly to give you an answer, okay, we ask the model to produce the intermediate steps. We can do zero shot chain of thought, we can do a few shot chain of thought. For example, on the right hand side, we have a question and an answer. Alex has 5 cakes, she got two more and gave four. How many cakes does Alex have? um, we can say the answer is three. We can give few more examples, 2 3 examples, and then we can give a new question to the model and ask for the answer. So it will just give us the answer. But if in our examples we just don't give the final answer, we also give the intermediate steps, the models tend to do the same. They also try to explain the answer. Okay. So this step-by-step reasoning help us improve the accuracy. That's how we know that it is actually helping. It makes the model more transparent, interpretable, and it also definitely helps us debug the model. We understand better what the model has learned, especially in terms of human alignment. It's very helpful when we know how the model is perceiving things. Um, Let me give you an example and then discuss a bit more. As I said, so you can also do zero shot chain of thought. Zero shot chain of thought is when you don't give any example to the model, you just give a question and you ask the model to think step by step. Just by asking things step by step, the model do this chain of thought thing and can come up with a better answer. And so on the right hand side you can see the results. It gives a big jump, even with zero shot chain of thought in some cases. But why does it happen? Why is it happening? So the issue is that large language models, unlike humans, mostly humans, when you ask a question, humans can build the abstract model of the problem and the world in their mind. They can come up with their answer and then they start communicating that answer. Okay. So someone asked a question, I resolved it in my mind, I know the answer, and then I start talking. That's normal for humans. For large language models, that's not how they work. As I told you, they are next token predictors. When they start generating the answer, they don't know the final answer that they will spit out. Okay. So for example, here if you ask a large language model, maybe now it will give the correct answer, but this was last year. What is the largest state bordering Mississippi River? It just starts generating these tokens. So and come up with an answer that um, which one is it? Yeah, Louisiana. Okay, the largest state bordering the Mississippi River is Louisiana, probably because the border that it shares with Mississippi River is the longest. Probably that's the reason, which is wrong. So we ask the model, don't give us the direct answer. We don't want direct answer. We want step by step answer. Okay. Now it can do, first list the states that border Mississippi River, then it can compute the size of those states, and then it can find the states with the greatest area, and then it can say Minnesota is the largest state bordering Mississippi River. Okay. So as I said, so when large language models start giving you the answer, they don't know the final answer. They are coming up with the tokens as they go, as they go, okay, on the fly. So, so coming back to the question, are LLMs able to reason? Okay. So this is still, like, even no matter what we say, it remains a very difficult question to answer. Um, there are a few issues that I'll explain, but in short, LLMs do perform very well on many benchmarks these days. Okay. And if these benchmarks are any criteria for how good they are doing on reasoning, then definitely LLMs can do better than non-expert humans, at least, and in some cases even expert humans on many benchmarks. These benchmarks range from mathematical reasoning. There is Hella Swag, which is sentence completion benchmark. There are graduate level school questions. Okay. Um then there is benchmarks like Big Bench Hard, which consist of many smaller subtasks. Okay, which range from all the way from world knowledge based reasoning to algorithmic reasoning and so on, common sense QA. So if you look at the benchmarks, like around on the range of benchmarks, the LLMs give very good results now. um, but there are a few things that we must keep in our mind, that there can be some issues when we evaluate LLMs on these benchmarks, and there are new better benchmarks coming, um, like recently there are few, and of course in near future we'll see a lot more of those that evaluate LLMs much better than these benchmarks. The reason with these benchmarks are that they are mostly templated. They are pre-LLM era benchmarks. Okay, they don't show if the model is actually reasoning or is it retrieving something, because the models have seen a lot of data during their training, especially pre-training step. So we never know if they're just retrieving that information or if they're actually doing the reasoning. And similarly, they might exploit some artifacts in the data that humans don't see, but these models can exploit that. Okay, it can be as simple as some symbols that appear when the answer is correct or wrong. Okay, so something like that. These models are very good at exploiting artifacts. On the other hand, humans usually ignore those artifacts. And another issue is many of these benchmarks focus on math problems. So in a way, LLMs keep getting better at those problems, but you train LLM, it's very good at math problem. When you apply it to your own problem, they give very bad performance. So all that, it's a complex question to answer. Yes, they can do reasoning, but there are a few confounders that you should be aware of. So how to improve reasoning in LLMs? We surely saw the benefit of reasoning with LLMs. They can do a lot of our tasks. We like when they give the explanation. How can we improve that? So there are a lot of trends that are emerging right now. One is model scaling versus efficiency and efficiency. Uh, when ChatGPT came, there was an understanding that reasoning is an emergent property. It will be there in the bigger models, but it will not be there in smaller models. But recently, we have seen very good quality models, which are 3 billion parameters, 8 billion parameters, and they are amazingly good at reasoning. Although we can always argue that they were trained using data distilled from bigger models, but still, these models themselves are very small, right? So we there is a preference of using smaller, more efficient models that we can do very cheap inference on. uh, Distilling is becoming very common, where we have a bigger model, we generate synthetic data using that model, and we use it on smaller model. And then quantization to save space, sparsity, mixture of expert models, where we have multiple smaller models. All these research topics are going on very actively. um, there is a trend on building domain specific, problem specific models also. So we don't want our models to be too general. We just want it to solve within the domain that I care about. Context length, how long context length can be handled, memory mechanisms of these models. Then alignment is a very active space, where we are trying to reduce um, the amount of labeled data that we need to align these models to human preferences. Okay, agentic behavior, I'll talk about agentic behavior. And then there is a trade-off between real time versus accuracy trade-off. So for reasoning, do we want the answer immediately, or can we give some time to the model to think, for the lack of better word? So the models are not thinking in that way, but can we give some time, or we need the answer in real time? So there is a trade-off there. um, so in order to generate high quality data, so there are few few things that we can do. First of all, for instruction fine tuning phase, we can gather very diverse data from various sources. Again, these sources can come from uncurated sources, can come from internet crawl data, but we have methods to cure them. We have methods to use that data to create better quality synthetic data. um, Transformation of existing data sets that are mostly pre-LLM era data sets, augment them with new data, and pure synthetic data generation of data, of like new data that is not based on any existing data set. That's another thing we're looking into. Extreme filtering of the data. We have already seen that we don't need million or tens of millions of data to fine tune. A very small size like 10K very high quality data is better than 1 million medium quality of data. Okay. um, then of course hyperparameter tuning is a huge issue. When you have data from multiple sources, how to mix, in what ratio should it be mixed. Okay, so that's all becoming very important. And going beyond that, as I said, alignment, and recently reinforcement learning methods are being applied to make the search very efficient during the inference also. I'll talk a little bit about that, and so on. When we look at reasoning from another point of view, there are two kinds of tasks in the reasoning space. um, One is where we can call them algorithmic tasks, okay, that are rule based, can be written as a code most of the time. Okay, then there are non algorithmic tasks that may need the model to have world model, um, abstract world model, abstract understanding of how common sense works. um, so these are two very different tasks, and we need very different methods for improving algorithmic tasks and very different methods for improving non-algorithmic tasks. Algorithmic tasks, for example, include math problems, sorting, optimization, coding, and non-algorithmic question answering, comprehension, summarization, any advice. So that all comes in under the category of non-algorithmic tasks. And we are always like, whatever method we use to generate data, we need to consider which one of these category it will improve. So for example, there are methods called self discover, where what they do is they ask the model, they prompt the model to pick up the best reasoning strategy to solve the question, and break down your problem into smaller problems, and then implement that reasoning um, to solve the problem. Okay, this self discover is very good for non algorithmic tasks, although it does show some potential for algorithmic tasks. On the other hand, there is another paper called chain of code, where they generate, just like chain of thoughts, they generate a code and they execute the code, um, with Python and without Python, like using LLM, and they can solve the problem, and they show a big improvement um, over simple chain of thought. So chain of code mostly target algorithmic tasks. Okay, it will not perform very well on non-algorithmic tasks. Similarly, a lot of knowledge has been encoded like manually over decades by humans in knowledge graphs, and knowledge graphs are right now kind of untapped resource that we can leverage. As we know, LLMs have been pre-trained on a lot of unstructured text data, but knowledge graphs have mostly been ignored. And the reason is that training on a very templated knowledge graph, triple data, will basically prove to be very toxic for these models. These models don't like seeing similar pattern again and again during training, and that's exactly what knowledge graph will do. So one idea is that we leverage knowledge graphs to generate very high quality data that is grounded in the knowledge that is decoded by humans over the decades. And especially in some domains like financial domains or other domains, these knowledge graphs can play a big role. In chemistry, in biology, these knowledge graphs can play a big role in improving the quality of large language models. um, and this is an area you can keep looking for papers, and we'll see much more in the coming months. Going beyond chain of thought. So chain of thought, very easy, very simple, makes sense. We should always be using it. What's beyond that? Okay. uh, we know like there is direct, like asking input and going to output, input with steps and then output. It can be very simple approach to improve the quality. For example, self consistency, where we run multiple chain of thoughts. So this one, if you can see my cursor, you see multiple chain of thought, and then you see multiple answer, and then you do majority voting, and whichever gets the most votes is the right answer. This is self consistency, and this can be used at inference time. This can be used to generate very high quality data. And tree of thought, I'll talk again in the next slide probably. So tree of thought is where we don't generate one stream or few fixed streams of thoughts. It is where we generate um, multiple thoughts. We either search depth first or breadth first, and we reject some of the thoughts. We can go back in the thought process. We can explore a different branch, and so on and so forth. Okay. So the possibilities here, as you can understand, the search possibilities can be very huge. And for complex problem, they can tend to reach infinity. Okay. So what we need here is very efficient search algorithms. And this is another emerging trend, especially highlighted by GPT 4.01 preview, okay, where they came up with a very efficient algorithm to search through this tree of thoughts. So this tree of individual steps. Okay. Uh, the first thing that we want is that instead of knowing the final answer, we want to know how each step, what's the value, or what value does each step provide towards the final goal. Okay. That is something that we call process reward model. That is becoming very common. Instead of getting one reward for the final output, we can now think of getting reward for each step. And then there, all this is a search algorithm. And search algorithm, as I said, we can do breadth first strategy, we can do depth first strategy. But you can imagine, once this graph keeps becoming bigger and bigger, it's very difficult to do an efficient search with very trivial algorithms. So it's becoming common to train this search mechanism through reinforcement learning. um, it's also becoming common to hide these steps. So of course the final chain of thought maybe the human is interested in, but during this search there will be a lot of noise that will be generated. Maybe humans don't want to see all that noise. Okay. It can take a long time to going through all these search strategies. um, as far as I understand, it's both to prevent the noise and also to stop other people from distilling your model. If you open all these thoughts, it's very easy to understand what the model is trying to do. Okay. So that's another reason to hide all these thoughts. Um and the idea here is not to do too much of these very slow inference. The idea here is that keep generating very high quality from this very slow inference procedure, and feed that data into the next iteration of training. So we want our inference to be cheap and speedy, therefore we put this data into training. Let's look at this question, like, which one is heavier, 1 kg of cotton or 1 kg of steel? Maybe if we ask this question to a 4-year-old kid, it will be a very fun question for them. But to us, it comes naturally. The outcome, we don't even need to think about this. But if you ask GPT-o1 preview, I tried and it took 22 seconds to reply to this. Of course, it answered correctly, but it took 22 seconds of reasoning and very expensive compute. I don't know how many tokens, and then it reached the answer. So we see like where we give more time for the model to do search, and we expect higher accuracy versus real time and lower accuracy. So in a way, we are now we know that LLMs are very good at next token prediction, but we also, as I highlighted, there are few issues that need to be resolved. So we are moving towards what we call neurosymbolic systems, okay, where we have neural part and we have symbolic part also. We can think of agents as a neurosymbolic system too, if you want. So agents, for example, are kind of feedback kind of mechanism where we prompt the same model or multiple models multiple times to generate an output, to call a tool, to critique on its own decision, to correct its decision, keep looping until we are happy, the critic is happy about the outcome. Okay. Because it calls symbolic tools, it's even the verifiers can be symbolic. You can consider it to be a neurosymbolic system, and this is becoming much more common. Agents, of course, does not start with GPT 4.01. Agents existed before, and now I think they will even be catching more traction. So are we so as I said, so neurosymbolic AI. So we know that tool calling is becoming ubiquitous in these LLM model space. Okay. Search planning algorithms are also making a comeback. So we don't only want to rely on LLMs. Okay. We want to augment their shortcomings with symbolic techniques, which we have very good control of, which we know works, which comes with some guarantees. Okay. So essentially, I would say that we are going back towards neurosymbolic system. It can be at the inference time, it can be to generate higher quality data, but we are going to back towards neurosymbolic system. And it does not come as any surprise to me. Um, this is what humans do. Humans are very good at communicating in symbols. We always communicate in symbols. We manipulate symbols. We make world representation, abstraction of the ideas as symbols. Okay. So why can't AI systems do that? AI systems should also be neurosymbolic. Instead of expecting everything from a single LLM, um, there should be a combination of symbolic and neural systems, right? So human use symbols to communicate, but there are creatures seemingly in this universe that don't use symbols to communicate. And I hope you recognize the two movie scenes from Avatar and PK. Uh, they're like they can create a bond and they can just communicate with each other. And on the bottom, they can just hold hands and communicate. No need for symbols. But anyways, we are humans, so we are stuck with symbols, so we cannot communicate like them. uh it's a repetition. So what is IBM doing in this space? Okay, so this is with that I think I'll take another 5-10 minutes. uh, so what is IBM doing in this space? IBM is building its own series of large language models. It's called granite models. There are a whole series of model for language, for function calling, for coding, for time series data, and all of them are available like openly in open space, in Hugging Face, in GitHub. And I'll introduce another project called Instruct Lab project, and I'll highlight a little bit what's the difference between IBM's way of working with open models versus other open models. IBM Granite models, I don't have a slide on that, but just to let you know, one of the big difference from anything that is available in the market. First, they are very competitive models. Okay, they perform very well. Secondly, they are the only models that come with full transparency on what data they were trained on. So, and they are enterprise grade in that sense. Also, the size is small, so the inference time will be much better than anything you run with the bigger models. Okay. On the right hand side, if you say like IBM and Meta have co-launched something called AI Alliance that promote this open community kind of uh, management of these large language models. And on the left, like you can see that open source LLMs exist already. We use them. We are aware. Probably Hugging Face have over several 100K open models now. But are they really open? Like we can use them, but we cannot contribute them. Open source systems used to be where you can see them, but you can use them, but you can also contribute towards that, right? But that's not what the open models right now are doing. But IBM is trying to change that. uh, IBM is providing a mechanism where people will be able to contribute to the large language model building also, not only come at the last step as a user. Okay. Similarly, the ability to contribute new ideas, of course, you can always build your own open source model, but that comes with a lot of expertise. So that's another thing that we are focusing, how to make it easy for people to contribute. Okay. And governance practices around the large language models. So in Instruct Lab, what is allowed, what we allow the community to do is to add additional skills or knowledge to the repository of existing skills and knowledge. Okay. It's model agnostic. Instruct Lab, what it does is that it picks up those skills and knowledge that are contributed by the user, and we generate very high quality synthetic data on that using some bigger model, and we train the next iteration of the model in that skill and in that knowledge also. So in a way, if the current generation of the model is not good at the domain that you want, next generation you can be sure will be much better in that domain. And there is already a taxonomy that exists of many skills and many knowledge based skills and foundational skills, compositional skills. Okay. And the idea is that instead of, if you look at the right hand side output distribution, the idea is that if you ask the model to just generate synthetic data without any guidance, it will just try to generate the kind of synthetic data that is very much aligned with the distribution of the teacher model. But when we give a taxonomy, when we try to give a very broad area of inputs, the model will tend to generate the data across the distribution, not only uh, very narrow in the scope. Okay. So that's the idea, and we saw benefits of this on various models, including open source model, IBM models, and so on and so forth. So this is a project that you can look more into, and if you want, as I said, you can contribute through creating new skills, providing new examples, and so on. Okay. There is another project where you can also contribute new data generation pipelines, but I'll not go into that in this presentation. So let me give you an example, just like my last few slides, an example of what the application of reasoning with LLMs can look like. Okay. Uh, this is a project that I did back in 2017. It's a robotics project where we try to teach the robot some task. I'll play the video. Let me know if you hear the sound.
No, your sound is not visible.
I will teach you peg assembly task.
Oh yeah, now we can hear. Yeah.
Okay, okay. So I'll play it again. I will teach you peg assembly task. Observe the initial state. Okay, I will check an initial state. I have observed the initial state. This is the final state. Okay, I will check a final state. I have observed the final state. Okay, I understand the PEG assembly task. Please confirm the plan on my screen and validate. It's okay. I will check an initial state. I got the initial state. Implementing plan on the manipulator. Everything is fine. I will go back. So this is a project that we did like in back in 2017, and you can see that one robot is learning something, it's teaching another robot. This peg insertion task is what the robot has already learned previously. We use reinforcement learning on an actual robot to teach it. But the thing I want to highlight, the most difficult thing here was the language part of it. Okay, so how do we tell something to the robot, um, and can the robot break it down into smaller commands that it need to perform? And that's exactly what we were not able to do at that time. There was nothing available, and in the end the solution was to make everything very templated, although it feels like natural language communication, but it is actually very templated. Okay, and if I were to do this project again, I would be definitely using large language model to understand the language and break down into smaller steps that the robot can actually perform. Actually, there is a paper called SayCan, and this SayCan paper combines low-level skills with large language models. For example, we in the previous um, use case, taking a picture is one skill. Insertion peg holding up picking up the peg is one one task or skill. Inserting the peg in the hole is another skill. So all these skills can be taught separately, and then I can ask the robot questions like go insert peg in the hole, and it can do kind of create an abstraction like possible next steps that it can take. As I said, LLMs are good at coming up with the next steps. Use those value functions like which is the best action to take in the very next step, and so on and so forth. It can perform that task very easy. Maybe not in the exact pattern that I want, but maybe it can do that. So, and the best thing about LLMs is that it's very easy to prompt them also. um, you don't need to come up with a very fancy framework. So here you can just say I would and give one dot, and then it can come up with the best options out of the options that are available to the robot. Okay, so this is a very good application of reasoning where it can reason in a neurosymbolic way, because the value functions, the values can be treated as a symbolic input, and the next possible action can be treated as a neural, and this neurosymbolic with LLM can work very well to solve very complex problems. So conclusions, LLMs have shown remarkable uh, capability for informal reasoning. Again, I'm not talking about formal reasoning, I don't want to go there even. LLMs will never replace calculators. They are not there to replace calculators. They will never replace planning algorithms. That's not their goal. Okay, so we should always talk about informal reasoning. There are definitely limitations in their capabilities, especially we have to verify whatever they generate. We usually have to verify that is it correct or not. That's a huge limitation. We are not able to trust these LLMs output. um, they don't come with any guarantee, so this is a big issue. How to improve LLMs? I explained few methods to you. High quality synthetic data, the concept of openness that comes with models like IBM Granite series model, IBM approach to open LLMs, where we allow the community to contribute to data generation and then training of the model indirectly. And finally, going towards neurosymbolic approach. We know neural, which is LLMs, are good at something, augment them with symbolic approach, which is good at something. The easiest thing that we can always very quickly imagine is combining LLM with a calculator. Okay, why do we need LLMs to learn all the mathematics when we have a simple calculator available that the LLM can call? Okay, so combine these systems together to come up with something that is much better, much more reliable, much more trustworthy. And that is it. So there are a few ways to connect with me. Feel free to connect to me, reach out to me. Thank you.
Thank you, Dr. Munawar, for such a wonderful talk. So now we will open the panel for questions. Let's see. Yep. So we have yeah. Um so yep, we had some audio issues because of the microphone, but it was audible from our side. Yeah. So one first question, how do you foresee the role of neurosymbolic AI evolving in the next generation of AI systems, especially in the context of reasoning and planning?
Yeah, that's a very good question. And as I said, so it was always there. It just got highlighted with GPT 4.01. Okay. So the role I see for them is um, or like making the base LLMs better. Okay, so of course doing this reinforcement learning kind of thing at inference time definitely helps, but how can we generate much better quality of data with these techniques, and we can feed it into the large language model to make them better at first place. But as I said repeatedly, LLMs are not there to replace planners. The planners will be planners, they will stay there. Reasoners are reasoners, they will always be there. It's only how these two can work together. So the interface part of these is where we should focus on. um, for example, like the capability of calling these planners, creating the output in the proper format, that is what we should be focusing on.
Oh, I'm sorry, I speak on mute. Yeah. So we have another question from Sushant as well. Like, how do you ensure that the efforts to improve LLM reasoning also consider the ethical aspects such as bias and fairness in the AI systems?
Yeah, again, that's a very good question. There is an aspect of human, like the alignment with the human preferences. Okay. Unfortunately, that is not directly addressed in creating these reasoning, reasoning data or reasoning evaluation. One thing we can definitely do is come up with better benchmarks. Okay. Right now, we are chasing most of the benchmarks that are pre LLM era, so they don't consider those social aspects or human preferences in that sense. Okay, but coming up with better benchmarks are definitely is a way where we can see if they really understand or if they really act the way humans want them to act. But the alignments still remain very very important. So we can train the data with whatever we want, but in the end that model will have some issues that needs to be resolved with minimal human alignment cycle. Okay, with minimal data. So that still remains, so those issues will remain there. Yeah.
All right. Third question is by Ray Bernard. Yeah. So does InstructLab use a vector database to store and retrieve the embedding of new knowledge?
uh, of new knowledge. What do we mean here by new knowledge?
By knowledge graph, I guess, like, if Bernard, you can like put it in the chat.
Yes. How can I see the chat, by the way? Should I stop sharing this?
Yeah, sure. If you feel.
And chat, okay. Does InstructLab use a database to retrieve embeddings of So the thing here is that new knowledge is for now stored as a natural language. Okay. So and it's embedded into the space whatever the LLM embedding we are using. Okay, at the runtime, but it's stored as a natural language for now.
Okay. So yes, there is another questions like, what do you think, like, what are the main limitations of current LLMs in reasoning landscape, and how can advances like IBM Granite help overcome these limitations?
So the major limitations of LLMs on reasoning is that as soon as we go toward complex reasoning questions, the LLM's performance just nosedive. Okay. So for example, you are doing a math question that involves 5 steps. LLMs may perform reasonably well. On one step, they will do very well. But let's suppose you go to 10-step math problem, they will be very poor. And this is very interesting research by Professor Rao also, who works on planner and LLMs. He showed that even O1 preview, after 14 steps, it just goes to 10, go to a zero. Okay. So how can these long chains still be solved by LLMs with reasonable accuracy, with human level performance? Okay. I think that's where we should be looking next. Very simple problems, I think it's become now saturated. All these benchmarks that are very trivial pre LLM era, I believe they have just saturated. We cannot get anything more from them. We have to come up with better benchmarks.
I'm sorry, again, I was speaking on mute. So we have another question by Muhammad Asaf. What is the potential of the neurosymbolic system to improve, especially in AI planning? And what are the best strategies to improve planning capabilities in LLMs?
So neurosymbolic, the issue with neurosymbolic is that the definition of neurosymbolic is too broad. Okay. There is a neurosymbolic where we go with probabilistic systems and combine like Markov decision processes and stuff. I don't want to go there because they don't include LLMs as such. Okay. So I want to define neurosymbolic as something that is working, some symbolic system that is working with LLM. Okay. And the best thing we can do is, if we have a system available, we can make sure. I actually had few slides where I was talking about function calling with LLMs. I don't know why I removed them. So function calling, tool calling, LLM should be able to call the right tool at the right time with the right parameters, right slots, everything. Okay. So that is a very interesting area to focus on. So once they are able to call those tools, we can get some guarantees that LLMs will be able to solve some problem. As I said, so let's suppose a math problem is involve 15 steps or 20 steps. Okay, if the LLM can call the right tool, we don't need to worry about how many steps there are in that problem, right? So that is where I believe the we need to focus on. And the other thing is the planner and the reinforcement learning. It's becoming very clear that they can directly help LLMs come up with better search algorithm when they're generating reasoning steps, or either at inference time again, or while they generate synthetic data, more synthetic data where the teacher model is distilled to create data for the smaller model training. Okay. So two things: better tool calling, help in generating better outcome by improving search algorithms. Okay.
All right. So we have another one question that's like from my end. So uh, the development is two faceted. Like one side, like we can see there are like newer models coming up with higher hyperparameters like 80 billion, 100 billion. So one side, like the models are increasing in side and computation, and the second side is like there is also a huge research going on in the architectural side, like changing the architecture from transformer, like with experimenting with like logical neural networks and the symbolic, integrating the symbolic models approaches with the transformer and this LLM architectures. So sky is the limit, like for we can't keep increasing the size forever. So what do you think, like the architectural side would be like the main drawback or the main thing the research community should focus on, because data and everything is like growing every day, but where to stop?
Yeah, I strongly believe that architecture will be the area where most of the innovation will come in. The reason why everyone went after transformer architecture without even thinking if this is the optimal architecture or not, because the previous architecture we faced problems like vanishing gradient, okay, and parallelism with GPU, because there were some architectures that were not very easily parallelizable. So when transformer came up with an architecture where we did not have very severe vanishing gradient problem, we did not have very issues with GPU implementation, everyone went after it and just apply all the energy, all the brute force there is in the world to solve that. But we can always think like there can be there was recently a very good blog by um, Liquid AI or something. I forgot. Maybe someone remembers. But that's a startup, I believe, out of MIT or somewhere, where they showed that much smaller models can perform like a lot better um, with a different architecture. So any architecture that can support this efficient training with GPU does not have gradient vanishing problem, I believe, can potentially be explored. Okay. um, Attention mechanism, of course, we understand it plays a big role, but even there are now newer versions of attention that are much more efficient. At the same time, the thing is that, okay, we can create smaller models that are very efficient, but almost everyone understand that synthetic data is extremely important. Okay. And we always, in the near future, we will need teacher models to guide us. Okay. The reason is like the smaller model comes up with an output and we want to find out if the output is good or bad. The smaller model want to find out. We cannot put a lot of human annotation effort for every single model that we have. So the strategy is that we make a very good bigger model, we put a lot of resources into it, we put a lot of human annotated data, so the bigger model understand human preferences. um, it understand a lot of different domains. It takes like, it's very expensive to run, but it's very good. Okay. And then we create smaller models that are very efficient to run. They can run on the edge on your phones. Okay. um, we don't want to do human annotation or anything again, so we just distill the larger model to build the smaller models. Okay. So I think both will be there, but we will always be using the smaller models, not the larger models for our normal use cases. Okay.
Sure, that answers my question. So does anyone have any more questions, or also for the virtual audience here, please feel free to like put on the chat. Otherwise, like we'll end our seminar for this Friday.
I heard there is pizza also, right? So I'll miss the pizza.
Yes, we have pizzas, but yeah, we'll be sending you a token of appreciation, like a gift. from our end, like at your place. Thank you so much.
Thank you so much. Yeah, enjoy your pizza. Enjoy the discussion.
Yep. So anyone? I think, yep, we are good. So thanks everyone for showing up. Thanks, Dr. Munawar, for giving us a wonderful talk this Friday. So please feel free to like reach out if you have any more questions. You can reach out to him over LinkedIn, and he's very active in social media. So you feel free to like connect with him. Um,
Yeah.
yep. Thanks everyone.
Thank
Thanks.
you once again for the invitation also.
Yep. No problem. Our pleasure. Thank you.
Thank you. Bye bye.
Bye.